anche un po' di più.
Ok.
Ok, so buongiorno a tutti and a virtual welcome from our beautiful Aula Magna. It is my great pleasure to open the new season of the DFA colloquia with Professor Luca Cipelletti from Montpellier University. Professor Cipelletti graduated in physics and got a master degree in physics and a PhD in physics at the University of Milan. And then he did a postdoc with David Weiss at UPenn and Harvard University. And then he moved to Montpellier, where he is now professor of physics and also director of the laboratory of colloids, glasses, and nanomaterials of a local CNRS. His research interests concern the experimental investigation of glassy soft matter systems whose constituents interact via attractive forces, thereby forming a network as in gels or are crowded as in concentrated colloidal suspensions. For his studies, he has also been involved in microgravity experiments carried out in space missions sponsored by NASA and the European Space Agency. In today's colloquium, Professor Cipelletti will discuss the so-called yielding transition. That is the transition from the solid to fluid state induced by mechanical stress in the case of colloidal systems. This fascinating transition is present in many disordered materials, including many of common use, such as toothpaste and hair gel, and its physical origin is the subject of intense studies and active research. Before I stop, just a brief announcement. I'm proud to announce that the next DFA colloquium will be held on November 16th by Professor Adam Rees, recipient of the Nobel Prize in Physics in 2011 for the discovery of the accelerating expansion of the universe. And now is your turn, Luca. The floor is all yours.
Okay, thank you very much, Gianpaolo, for the kind introduction. It's going to be tough to sort of be the one before Nobel Prize talk, but I'll try to do my best. So let me share my screen. Okay, I think it should work now. So I will tell you a little bit about the yielding transition of soft glasses, and this is work that has been done mainly by Stefano Aime, who was at that time a very brilliant PhD student with us in Montpellier. Now he's a junior professor at ESPCI in Paris, and Domenico Tozzolillo, who is a young colleague, CNRS colleague here in Montpellier. And the other people involved are Dave Pine from New York University and Laurence Ramos, also from Montpellier. So my talk will be about soft matter materials. So I thought that perhaps I should spend a few slides saying what soft matter is. And I like very much a definition that Dan Frankel, who's a very famous and a great person in theory and simulations, gave many times. And basically what Dan said is, okay, soft matter, it's easy. It's basically the stuff that you're not supposed to bring in an airplane. So liquid, gels, foams, all these kind of materials. And if we go to a more physics-related definition, it's soft matter is one kind of condensed matter systems. And the point which is really important for the following of my talk is that these soft matter systems, as the name tells us, they are easily deformed or altered by either thermal stressor or mechanical stressors that are quite small, of magnitude of thermal fluctuations. So quite generally, there are many ways one can classify soft matter systems. This is just one of these ways. It's this sort of magic triangle where we have on one corner colloidal particles. Those are solid particles for example, made of polystyrene or silica or other materials that are suspended in a background fluid, many times just water or more complex fluids. And because these objects are typically on the micron or submicron scale, they undergo a Brownian motion because of the collisions of the molecules in the solvent against the particles, as is shown in this movie here. We have also active colloids that are quite popular nowadays, where one can use chemical reactions to actually make these objects move much faster and in a controlled way, much faster than what would be just with Brownian motion. Other typical constituents of soft materials are polymers that are shown here, or self-assembled systems based on molecules that are called surfactants that have parts that have a different affinity with the solvent, like a polar head which has a high affinity with water, and a non-polar tail that has a greater affinity with apolar materials like just air or oil. And this is basically the kind of molecules that we find in all detergents. And then soft matter is also, I mean, the concept developed in soft matters are often useful to tackle some problems in biology, where one can see biologically relevant objects such as a cell as made of building blocks that are these colloids, polymers, and surfactant systems. In my talk, I will be concerned with soft matter systems, which are essentially mostly solid-like and are amorphous. So these amorphous soft solids are just one example of a variety of amorphous systems that span different time scale, length scales, characteristic length scale from sub-nanometric or nanometric length scales in hard condensed matter amorphous systems like metallic and silicate glasses, up to millimeter or even centimeter scales in granular materials up here. And all these systems share actually many fascinating similarities. And what I will be dealing with are colloidal glasses, so dense suspensions of colloidal particles that are amorphous, they don't have any crystalline order, and where the constituents have a typical size of the order of a few hundreds of nanometers. And this is the kind of thing that you find in your toothpaste, for example. So these systems, because are on this micron or submicron scale, are fully thermal systems for which Brownian motion is sort of the engine that is responsible for the evolution of the dynamics of the system. So as you know very well, these soft amorphous soft materials can be easily flowed. This is what happens if you apply a large enough perturbation, for example, to your toothpaste when you squeeze it to spread it on this stick here. And you know very well that large perturbation, actually, it's not very large in absolute terms. The forces and stresses that are at play here are quite modest. But this is large in the sense that you need to go beyond a minimum threshold of stress applied to your material in order to make it flow. Otherwise, if you let it just sit there, for example, under the action of gravity, which also applies a stress on the system, well, this gravitational stress is not large enough in order to make your system flow. So there is a yielding transition from a fluid-like state, or rather from a solid-like state to a fluid-like state, which is controlled by the amount of stress which is applied to the material. And this yielding transition is something that we find across a variety of soft solids that we encounter in everyday life. It is very important for the use properties of these materials, and it has also quite an important relevance for more fundamental aspects, because as I will show you, this is a transition which is not very well understood yet. So let me just spend a word about how we typically probe the mechanical properties of these soft solids. We do so with rheology, and rheology consists in basically in applying some sort of force on your system to deform it and measure the relationship between the applied force and the resulting deformation. This picture here illustrates rheology done in a shear geometry, and the relevant quantities are the shear stress sigma. This is the ratio between the magnitude of the tangential force which is applied to some surface A of the material and this area A. So this is the stress, and in response to this stress, the material will deform, and the deformation is quantified by the shear strain gamma naught, which is just the ratio of this elongation here, delta x, divided by the thickness of the material E. If you do this kind of experiment on a purely solid material, you deform it by an amount which is proportional to the applied force, you take the force off, and you recover the initial configuration. If you do it on a fluid-like material, you will induce a flow of your fluid. Most soft matter systems actually have a behavior which is intermediate between purely solid-like and purely fluid-like. And an interesting way to probe these viscoelastic materials is to do oscillatory rheology, which is illustrated here. The idea is that one would apply a sinusoidal deformation to the material. So gamma will be in time something like sinus of some angular frequency omega times t times an amplitude gamma naught of the applied shear. And the stress, which can be measured in response to this applied strain, typically contains a part which is in phase with the applied deformation and a part which is in quadrature of phase. So this in phase part corresponds to the elastic response of the material, and it is characterized by a coefficient G prime, which is called the storage modulus. It's basically the equivalent of a spring constant if you would do an extension experiment on a spring. The part which is in quadrature of phase with these cosine terms contains as a prefactor the so-called loss modulus G double prime, which describes the dissipative part of the fluid-like part of the response of the material. So what happens if we test one of our amorphous solids with this oscillatory rheology experiments? What I'm showing here is an example for a concentrated suspension of silica particles. And what is shown here is the storage modulus G prime and the loss modulus G double prime at a fixed frequency. This is roughly 1 Hertz as a function of the amplitude of the applied strain. So for small strains, we are in a linear regime where G prime and G double prime basically do not depend on the amplitude of the applied strain. And note that this is a log scale, so G prime is about 1 order of magnitude larger than G double prime. It means that the material overall behaves predominantly as a solid. But if you start applying a perturbation which is large enough, if you increase the amplitude of the applied strain, at some point you start observing deviation from linear behavior. G double prime, the dissipative part, starts growing, G prime goes down, eventually they cross each other, and at very large applied strains, you are in a situation where the fluid-like dissipative part of the response of a system dominates with respect to the solid-like part. So you have fluidized your material, you have gone past this yielding transition from solid-like behavior to a fluid-like behavior. And another way to characterize that is just to look at the stress response, which initially is linear with the strain and then flattens out when you are passing this yielding transition. Interestingly, we find that what I've shown you for these silica particles is not peculiar to that specific system, but is something that we find for a variety of different systems, like emulsions. Emulsions are drops of a liquid embedded in a different liquid. For example, drops of oil embedded in water and stabilized by some of these surfactant molecules that I've mentioned at the beginning. And microgels, those are quite popular systems. Those are polymeric gels, which are shaped in small spheres, again, of a micron or submicron size. And for all these materials, we have the same behavior with an elastic, predominantly elastic solid-like behavior at small applied strain, which past the yielding transition goes to a fluid-like behavior. So this is a common phenomenology, and people have proposed various models. For example, the soft glassy rheology model, models based on the mode coupling theory, models based on more phenomenological so-called fluidity approaches. And the sort of common framework in all of these models is the idea that by applying an oscillatory shear, one induces rearrangements, microscopic rearrangements in the system, and therefore accelerates the dynamics of the system, which will be essentially frozen in the absence of any perturbation, because we are speaking of solid-like systems, and promotes the transition to a liquid-like state. This can be framed in simple terms, as is done here, thinking of what happens to the relaxation rate, the structural relaxation rate of the system. The structural relaxation rate is 1/tau. Tau here is typically the time it takes for one of these constituents, a silica particle or an emulsion, to move on a length scale comparable to its own size. So this 1/tau, this relaxation rate, is the sum of two contributions. One contribution is 1/tau0. This is the quiescent contribution, the relaxation rate that you would observe for the system at rest. And then you have some additional contribution, which is due to the shear applied to your material, which is basically one can make reasonable assumptions. And one very popular assumption is that this additional relaxation rate is proportional to the strain rate. So this is the time derivative of applied strain, oscillatory strain, raised to some power mu. And indeed, this sort of relatively simple idea has been framed in a much more formal way with mode coupling theory, and have been used by Miyazaki and co-workers to explain the G prime and G double prime measurements in soft systems similar to the ones that I'm showing here. And as you can see from these blue curves that are the theory, these simple ideas sort of capture the main features of the rheology experiment. However, one would like to make the connection with the actual microscopic dynamics, because when we write something like that, 1/tau equals this and that, we are not actually, at this point, we are not actually measuring any microscopic relaxation rate. We are just making the assumption that there is some microscopic relaxation process, and that microscopic relaxation process obeys this ansatz. So people have started to do experiments where you try to probe at the same time the mechanical or rheological properties of your material under shear and the microscopic dynamics. There are not many works, because this is experimentally a little bit challenging, but there is a growing literature in the field. And the problem is that people find contrasting and contradictory results, and there is no clear picture that emerges from these experiments. One first contradictory thing is what is the relationship between yielding as observed on a macroscopic scale by doing a rheology experiment and yielding as detected more microscopically by measuring the dynamics of the constituents. So what is shown here are results for dense assembly of emulsion drops. And in this experiment, people have measured how far these drops were displaced after one full cycle. If the material was a perfect ideal solid, the displacement after one full deformation cycle would be 0 because everything will be perfectly elastically and you go exactly back to the initial configuration. But as a function of the applied strain amplitude, and for samples prepared a different volume fraction of droplets with respect to the total volume of the sample, one finds that there is a sharp increase of the mobility, the microscopic mobility of these particles at some applied strain. So one can easily define a yield transition at the microscopic scale. And if you try to compare when, for what strain amplitude that transition occurs, as compared to what you measure by rheology, it typically occurs, let me just go back here, it typically occurs at the onset of deviation with respect to linear behavior, so maybe around here. But well before the sample is fully fluidized, as indicated by G double prime that overcomes G prime. So this is what was found in this experiment. This other plot shows similar results for a similar system, but probed in a different way, where people have found that no, actually the microscopic yielding transition occurs at the same strain amplitude, where macroscopically you can observe a full fluidization of your system. So this is one first puzzling observation. We don't know exactly what's going on. Another puzzle concerns the nature of this yielding transition. Is it clearly it's not a thermodynamic transition? We are speaking of out of equilibrium system and dynamic transitions, but people have drawn analogies with first order phase transition or second order phase transition. And again, there is no general consensus. There are some experiments where people have highlighted features of this yielding transition that are reminiscent of a first order transition. For example, people have observed hysteresis. This is shown here in experiments where one measures the shear stress as a function of the applied shear strain rate, where here you're not doing oscillations, you're just imposing continuous shear with a given time derivative, a given velocity of shearing, and looking what happens if you do your experiment, increasing the slowly the shear rate starting from a quiescent sample, or the opposite way, from your maximum shear rate you go down, and you see that your stress doesn't follow the same curve. You have this hysteretic loop, and this is also observed in some cases if you look at more microscopic quantities like the velocity profile within your sample. This is something reminiscent of first order transition where one sees hysteresis. Other features reminiscent of first order transition is the sharpness of the transition. So these are experiments in the group of Denis Barthelot, who was basically pumping back and forth some concentrated emulsions in a microfluidic channel and looking if the drops would go back exactly to the same initial position after a full cycle, or if they would change nearest neighbor. And he quantifies this by introducing this fidelity parameter, which is basically the fraction of particles that do not change their nearest neighbor. And as a function of the equivalent of an applied strain, one sees a very sharp transition between a fidelity 1 state and essentially 0 fidelity state, where the sample is mixed up as a result of this pumping back and forth. So this sharpness is reminiscent of what happens in a first-order transition. And the other thing which is reminiscent of first-order transition is the fact that if you focus on the sample that has a sort of intermediate fidelity, this is due to the fact that you have the partitioning of the sample in regions that are either fully reversible, the blue regions, or fully irreversible, essentially. You don't have something smooth that corresponds to regions that are so reversible. On the other hand, in other experiments, people have highlighted features that are usually associated to second-order transitions. For example, here, people have measured the dynamical susceptibility. This is a quantification of how much fluctuations you have in the system, and approaching the yielding transition, one observes a great growth of these fluctuations, which is something often seen in second-order transitions. And in this other paper, people have studied with what is called a viscoplastic model. Basically, you assume that in your system, due to the shear, there is a plastic event, and the stress generated by this plastic event is redistributed everywhere. And by running the model, they quantify the rate of plastic events in the system as a function of the applied amplitude, the amplitude of the applied strain. And they find that this rate of plastic events does not jump abruptly at the yielding transition, but rather starts growing beyond a given threshold as a power law, which is reminiscent of second-order transitions. So clearly there is a need of new experiments, and this is what we have tried to do. And our approach was based on the idea of testing several systems, which I have already mentioned, using a variety of setups. I don't want to go into the details. Those are, in some cases, just microscopy. In other cases, light scattering setups. In all cases, those are setups that allow you to probe the microscopic dynamics on the length scale, typically of the particle size. And I think that our best asset was actually having Stefano, who was really a great student who performed all these experiments. So let me describe you a little bit these experiments. And the quantity that I will show you over and over is this intensity correlation function, which is measured in light scattering experiments. This basically quantifies, so for people who are familiar with the intermediate scattering function, this is just the square of the intermediate scattering function. And just keep in mind that this is a quantity that compares the system configuration at time t and time t plus some delay tau. And this intensity correlation function decays as a function of tau because the system configuration changes with time. And one means fully correlated configurations at the beginning when the system has not had time to evolve yet. And 0 means that the objects have moved over a distance, which again, it's comparable to their own size in our experiment. So let me first describe briefly what happens on a colloidal suspension at rest, so non-applied shear. If you take a very diluted colloidal suspension, you have an exponential decay of this correlation function, which is just the result of Brownian motion that these colloids undergo. If you start increasing the volume fraction, well, the decay time becomes a bit longer because particles are somehow impeded in their motion by the presence of the surrounding particles. And if you start having very concentrated systems, the decay time become much longer. Have a look at the x-axis. At the beginning, we were speaking of milliseconds. At the end, we are speaking of thousands of seconds. So the dynamics slow down by several orders of magnitude as a result of this interaction of each particle with the surrounding particles. So in a colloidal suspension at rest, the control parameter that allows to go from the Brownian case to a colloidal glass is volume fraction. Everything is driven by the crowding of these particles. In the rest of my talk, I will focus on systems that at rest are colloidal glasses. So they have an extremely slow dynamics, but now we start applying some mechanical perturbation to the system. And we do so basically with a homemade rheometer that Stefano has built. In this homemade rheometer, the sample is sandwiched between two glass plates, and one can apply a force or apply a deformation to a sample and measure the force, thereby doing what is normally done in a conventional rheometer. The reason why we built our own rheometer is that we wanted to couple it to light scattering. Schematically, to do this light scattering experiment, you illuminate the sample with a laser beam, and you collect on a CMOS camera an image of the light scattered by the sample. And this scattered light has a speckled appearance. You have these bright and dark spots. This is just an interference phenomenon because here on the screen you have the superposition of all electric fields scattered by each individual particle. The key point to keep in mind is that as particles move around, this interference pattern will evolve, so that by quantifying the temporal fluctuations of this speckled pattern, one can calculate the intensity correlation function that I have shown you before. There is a final important point to stress. All what I will show you has been measured with this so-called echo method. The idea is that you shear your sample with an oscillatory shear back and forth, and you take a speckle image every full cycle. Why do we do so? Because in this way, it is very easy to recognize whether some irreversible rearrangements have occurred in the sample. The idea is that if your sample was an ideal solid that didn't undergo any rearrangement after one or several cycles, when you go back to the same macroscopic deformation state, let's say zero deformation, then every single individual particle within the sample goes back exactly to the same position, and your spectral image is exactly identical to the initial one. If, by contrast, you see that your spectral image is not identical, well, that means that some sort of irreversible rearrangement has occurred within your sample. Okay, so this is what happens if you measure these correlation functions under shear. I'm plotting here first those data. Those are the data collected for the quiescent sample. Is sort of our reference curve. And now we start applying oscillatory shear with a growing shear amplitude. And what we see here is that if the shear amplitude is a few percent at most, there is a little acceleration of the dynamics. The relaxation time of these correlation functions becomes a bit smaller, but really nothing special occurs. In this regime, the blue curves can be fitted with the intermediate scattering function, can be fitted by this expression, which is called compressed exponential, because you have an exponential relaxation with this exponent 1.5, which is larger than 1, and which has been observed for many soft solids and even amorphous hard condensed materials at rest. Now, if you go in the opposite limit, where you apply a very large shear amplitude, you observe that your correlation function exhibit a relaxation that is accelerated by several orders of magnitude, and the shape of the correlation function has completely changed. It is much more stretched, and indeed we can fit the correlation function in this regime by what is called a stretch exponential relaxation, where the exponent is smaller than 1 and typically something like 0.5. For intermediate applied strains in this regime, we actually have a superposition of these two relaxation modes. And in this case, again, what is driving this transition from a very slow dynamics to fast dynamics is the applied strain. So we can rationalize for all applied strains, can fit our correlation functions with the sum of these two relaxation mode, a solid-like slow mode and a fluid-like fast mode, with this relaxation rate of a slow mode, of a fast mode, and chi here indicates the relative weight of the slow mode with respect to the total amplitude of the relaxation. And now what we will be interested in is to have a look at how these parameters, the fast and slow relaxation rates and the relative weight of the two modes, depend on the applied strain. This is what I'm showing here for one of our samples. So the blue points are the slow relaxation rate. As you can see, it is basically insensitive to applied strain up to a strain for this, in this case of 10% or so, and then it increases in the coexistence region where one observes two modes. The red points indicate the fast relaxation rate. It is not seen at small strain amplitude. It starts to be measurable in the coexistence region, and then it continues growing as a power law of the applied strain amplitude. And then the stars are just this relative amplitude of the two modes. Small gamma naught, you have only the slow mode, and then you have quite a sharp transition, which is at the microscopic level our yielding transition. And quite remarkably, we find that essentially the same kind of behavior is observed for all the three classes of systems that we have observed, in spite of the fact that they have different constituents, different interactions, and so forth. So this is a first indication that there is some kind of general scenario underlying what we have observed. Now, remember that we started with this ansatz proposed by Miyazaki and co-workers concerning the additivity of this structural relaxation rate. So we can try to plot, to fit our the data for our samples with this model. And what we find is that the model actually can capture pretty well the behavior at large applied strain, where the shear induced relaxation rate dominates completely everything. But it cannot really capture the fact that the transition is very sharp, and the fact that the slow relaxation mode is essentially insensitive to gamma naught over several decades in applied strain. So we have to go beyond this model and think of something a bit more refined. And this is really what I'm going to tell you about. And this is really something that Domenico and Stefano have thought a lot. So I think that the credit should go to that. So the way we have thought of our model is in terms of coarse-grained version of our sample, where we divide it in boxes and we say, okay, let's think of what is the relaxation rate of the ith box or ith site in our coarse-grained model. And the Miyazaki ansatz would consist in saying, okay, the relaxation rate is the sum of the relaxation rate at rest plus a term that depends on the external perturbation. But we already know that this doesn't work, so we have to cook up something different. And the idea that we throw in is the fact that the dynamics of the ith side must be somehow influenced by the dynamics of the neighboring sides, in the spirit of what people in the glass literature have proposed for dynamic facilitation. The idea is that if you are sitting in the side I, and this and that side have, by chance, faster than average dynamics, so they are more fluid-like, then this fluidity surrounding the ith side will help the ith side itself relaxing faster. And this is introduced in the model by adding here a coupling, a term that describes the coupling between side I with all the side j that are nearest neighbor of side I. And so this term involves the relaxation rates of the neighboring sides and some coupling constants between the side I and the neighbor sides j. And in the full version of this model, we assume that there is some disorder in the system, which we account for by assuming that these coupling constants alpha ij are drawn randomly from some probability distribution function, and we have checked that the details of this PDF are really not important. Now, we can study this model, but only with simulations, not analytically. If we want to get some insight on how the model works, we can go a step back and say, okay, let's start by studying the mean field version of the model, which would consist in saying, I take these coupling constants to be the same everywhere. So I have just one alpha parameter, which is the same for all pairs of sides. If one replaces this alpha ij by a single alpha and then reorganizes a little bit this equation here, one realizes that this can be written in this way. So gamma here is the relaxation rate under shear. Gamma rest is the relaxation rate of a system with no applied shear. Gamma naught is the amplitude of applied strain, n is some phenomenological exponent, alpha is coupling constant, and k is a parameter which is totally whose physical signification and importance and origin at this point is totally obscure, but I hope that I will show you that one can sort of rationalize it a little bit. So maybe some of you will have already noticed that this equation here bears a strong similarities with something that we know very well in physics, which is the van der Waals equation of state that describes a real gas. Van der Waals equation is written here: V minus V naught equal P plus some coupling constants V to a minus 2 equal RT. So we have an analogy between the relaxation rate and volume in van der Waals gas and this applied strain to a power minus n and pressure, and this obscure parameter k in our model plays the same role as temperature in the van der Waals equation. So driven by this analogy, we can plot our data in a way which is a little bit different with respect to what we would do normally. Normally, in an experiment, you apply the shear strain, and so the shear strain amplitude gamma naught is your control parameter on the x-axis, and then you plot on the y-axis the relaxation rate. But in order to make the analogy with the PV diagram of van der Waals gas, we want actually to replot the data in a different way, where you have the relaxation rate on the x-axis And on the y-axis, you have gamma naught to the minus n, which is the analogous of pressure in our model. So in this final representation, strain increases going downwards along the vertical axis, and the relaxation rate increases from left to right on the horizontal axis. Pretty much the same as in van der Waals PV diagram, we have families of curves that depend on temperature, in our case, on this K parameter. So we have iso-K curves that are shown here. And we have, for large values of the K curve, we have a smooth behavior, a smooth decrease of this gamma naught to the minus n with increasing relaxation rate. This corresponds to samples that are fully fluid, regardless of the fact that you apply or not a strain. So those are basically colloidal suspensions that are too diluted to exhibit a really solid-like state, even if the applied strain is very small. And then you have a sort of a critical iso-K line here, which is flat here, and then below this critical iso-K line, the model develops this non-monotonic behavior. And this non-monotonic behavior corresponds to the samples that exhibit yielding, because here at the beginning for up here, you have a small applied strain. So you have a very small relaxation rate. You are in the fully solid regime. You go down along this line, you increase the strain, amplitude, and the relaxation rate does not change significantly. At some point, physically, you have to jump on the other branch, because otherwise you would go in this region where this upward curve would correspond to systems that relax faster if you apply a smaller strain amplitude, which doesn't make any sense physically. So the system has to jump on the other branch, and the other branch is the fluid branch, where the relaxation rate increases steadily when you increase the applied strain. So in this framework, the yielding transition is the analogous of the transition between a liquid and a vapor state in van der Waals picture. This mean field version of the model has this non-monotonic behavior and doesn't predict the coexistence of the fast and slow relaxation rate that we have observed in our experiments. However, if we go back to the full model with disorder, where we have these coupling constants alpha that allow to describe in a more refined way what is happened locally, then this disorder smears out the transition, and there is a finite probability of observing the coexistence of the two relaxation modes. And this is shown here. So those are snapshots of simulations run by Stefano of these coarse-grained systems, where black and white correspond to slowly rearranging and fast rearranging regions under some applied shear. And you see that at very small applied shear, the probability distribution of the relaxation rate is peaked at a small relaxation rate. This corresponds to a solid-like state. At very high applied shear amplitude, you have essentially all sites that relax very rapidly. This is a fully fluidized system. And for intermediate cases, you have a bidispersed distribution of relaxation rate, which corresponds to the coexistence of a fast and slow relaxation mode observed in our experiments. One nice feature of the van der Waals approach is the fact that you can renormalize all your variables with respect to their value at the critical point, and draw a PV diagram which is sort of universal and applies to all systems. And of course, we can do the same thing for our yielding diagram. and we can use reduced variables where everything is normalized with respect to the value of the different parameters at the critical point. And if we do so, we can replot our curves. We have here the critical isotherm that corresponds to a critical normalized K equal to 1 by definition, and then above criticality and below criticality. And for curves below, for K values below criticality, we have this non-monotonic behavior, which we associate to the yielding transition. And if we determine the location of this yielding transition for various values of the K parameter, we end up with different regions in this state diagram that correspond to fully solid states, here in blue on the left. I'm sorry, my mouse is low. Liquid states in yellow above the critical iso-K, fluidized states in red where the applied shear is large enough to observe just one fast relaxation mode, and then the coexistence. And we can fit the model parameters in order to put all the points corresponding to the various samples that we have measured on this diagram. This is what we have done. I will skip a little bit of the details here. We can indeed find essentially what is the K parameter, the generalized temperature, if you wish, in this analogy with van der Waals, for the various samples that we have studied. And you see that this all our samples falls on curves that have a different K parameter. And it is tempting to associate the notion of glassiness, which is a bit fuzzy at this point, to the value of the K parameter, in the sense that we know that above the critical K, the samples are fully liquid, so they are not glassy. The glassiness is 0. And then when you go below criticality, deeper and deeper in this diagram, you make your sample more out of equilibrium, more glassy. So we may define this glassiness as 1 minus Kr. Kr is the relative value of this equivalent of temperature normalized by its critical value. And glassiness defined this way will be 0 by definition just at the critical point, and increase when you go deeper. Now this is nice, but one should check that this notion of glassiness makes sense, otherwise it's just a word. And this is what we have tried to do by comparing the behavior of samples of the same kind where we change just one parameter. So one first comparison concerns the samples of the same silicon nanoparticles where we change the volume fraction. And if you change volume fraction, you go from a suspension of 41% to a suspension of 45%. The suspension of 45%, it's deeper in this diagram, so it has a higher glassiness, which is consistent with the fact that people working with colloids know very well that as you increase volume fraction in a colloidal suspension, you get more and more glassy, more and more out of equilibrium. The same thing is observed for our emulsions, for which we have 4 samples at different volume fractions, with volume fraction that increases with glassiness. Another parameter that you can change is the frequency at which you perturb mechanically your system. And here the idea is that if you perturb your system at a higher frequency, the system is more out of equilibrium because you are going even faster than its spontaneous relaxation time as compared to what you would do if you go more slowly. So in general, one expects for glassy systems that the faster you perturb them, the more glassy they look like. And again, this is what we find. This glassiness increases as you increase the driving frequency. And the last parameter, which is interesting to look at, is the role of aging. So all these systems age, meaning that their properties slowly evolve with time. And this is something that is found in many glassy systems. And the general scenario is the fact that the system is out of equilibrium, and very slowly it explores an energy landscape and eventually finds deeper and deeper local minima of this energy landscape. And as it does so, its dynamics and other properties change and approach or move towards their equilibrium value. So in general, a system that has been aged for a while has lower dynamics, and so it is more glassy. And again, this is something that we find in our yield diagram, because if we take the same sample and we compare measurements for a young sample and age sample, we find that the age sample is more glassy than the young one. And perhaps the last thing that I will show you, because I am running out of time, is that we find an interesting correlation between glassiness, which we measure by mapping our experiments on this yield diagram, and the disorder in this coupling constants alpha ij. In this plot here, on the x-axis, you have the glassiness, and on the y-axis, you have the amount of disorder in these coupling constants characterized by the relative variance of the probability distribution from which these coupling parameters are drawn. And as you can see here, all samples follow a sort of common master curve, roughly, with increasing glassiness for decreasing disorder. So we find this relationship. It is at the end the amount of disorder in the coupling constants that dictates whether a sample is close to the critical point or, on the contrary, very far from the critical point, very deep in the glassy phase. So I think I should stop here. I had a few more things that I can show you if somebody has questions. Let me just summarize. So we have studied these soft solids under oscillatory strain to sort of try to quantify and understand the yielding transition at a microscopic level. So we have a common phenomenology. We have this idea that shear-induced dynamics are responsible for the relaxation of these systems. And we have shown that in order to rationalize our observations, you have to go beyond the assumptions that were made so far in the framework of mode coupling, namely, and we have proposed this simple model which has a fascinating analogy with van der Waals equation of state. This allowed us to draw an analogy between temperature in van der Waals and this glassiness parameter that rationalizes the different behavior of samples according to their volume fraction, driving frequency, and aging time. And with that, I would like to thank my collaborators, people with whom we have discussed quite a lot, funding agencies, and of course you all. And I would be happy to take questions if you have questions. Thank you very much.
And so, thank you very much, Luca, for this clear and inspiring talk. And now let me see if there are questions. Let me tell the audience. So either you can raise your hand, or you can write a question and I can read it later on. So let me first, so here I see Giulio, if you want to ask a question.
Thank you, Luca. It was a fascinating presentation. I was curious about one thing. So if I understand your presentation, you can go from the fluidized, let's say, state to the solid state, or the other way around, either having coexistence of the two states or avoiding it, right? Both are possible, or
so in the model, if you take the full model, in principle, you always have coexistence, except if you are very close to the critical point. Because basically the coexistence region, let me go back. Yep, the coexistence region will be here. So if you are very close to the critical point, the coexistence region will be shallow and small, and it will be larger if you are deeper in this region here. But in principle, you always get the coexistence. In the simplified version of the model, where you drop the disorder and you have the van der Waals-like stuff, you don't have coexistence. You jump from one branch to another branch.
I see.
In the experiments, in practice, we always see coexistence.
I see. Thank you.
Okay, so if everything is clear, we can move to the question by Matteo Pierno. Please, Matteo. Oh, sorry.
Can you hear me?
Yes, we can.
Yes,
Okay.
Ciao Matteo.
Ciao Luca, thank you for your exciting and inspiring talk. I have many questions, but I have to choose one. About the analogy with the phase diagram of the van der Waals equation of state. What is the analogy? What is exactly the analogy of the system, of your system, with a critical point? And also, can you define something similar to the surface tension between the liquid and the glassiness state?
Okay, yeah, excellent questions, very nice questions. This is something that we would like to do in the future, exploring what happens as you approach the critical point. In principle, so I didn't have time to show that, but for samples that are closer to the critical point, let's see, this is moving away, this is moving to a critical point. You do see things that are reminiscent of a second order like transition. You see large fluctuations in the relaxation time. You see sluggish dynamics in the sense that it takes a huge number of shear cycles to attain the stationary state. So there is clearly something interesting happening as you approach the critical point, but we didn't explore that systematically yet. As for the second question, this is also a very good question. I don't know, honestly, how far one can push the analogy and what would be the equivalent of surface tension and how this surface tension would behave as you go closer to a critical point. I know that Stefano and Domenico are still thinking a lot on the theoretical side of the story, and they may have some new ideas and thoughts on that, and maybe you will see them at some point pop out. But yeah, I don't know. At this stage, I have no precise answer to that.
Okay.
Thank you, Luca.
Okay, so are there any other questions? So everything is clear? No curiosity, whatever? So just I have in the meantime, if someone is thinking of a new question, are you planning to do this kind of experiments also in microgravity, or do you think this may affect the results or not?
Okay. So am I planning? Yes and no, in the sense that we are involved in an experiment with ESA, where there won't be a rheometer coupled to light scattering, but there will be a light scattering setup where you can drive your sample thermally with basically heating it locally with an infrared laser. This is a trick from Roberto Piazza's lab. So this is, and we plan to do things like cycles and stuff like that. So this is somehow reminiscent. I mean, somehow in line with this sort of thing. And the other thing is that in principle, we are involved in some collaboration with Chinese scientists who are sending to a Chinese space station a rheometer coupled to a microscope. So we hope to be able to do some experiments in microgravity. But it's always a little bit delicate, this kind of collaborations. You never know if things really happen and when and how and so forth. Concerning the role of gravity in these experiments, honestly, I don't think that gravity plays a major role because of two reasons. One is that the systems are quite dense, concentrated, so they are solid-like, and gravitational stresses don't really affect them that much. And the other thing is that some of these experiments were performed with a shear cell in the horizontal plane, and some were performed with a shear cell in the vertical plane. And we don't find any systematic difference between these two classes of experiments. Everything is basically fits in the same picture.
Okay. So let me see if there are no other questions. I'd like to thank again our speaker, and hope to see you soon live here in Padua, Luca.
Thank you very much.
Thank you very much again.
I'm really sorry that I couldn't come in person this time, but yes, I would be delighted to come and visit the department at some point.
Okay. Thank you very much, Luca.
Thanks again. Bye-bye.